Welcome back, Marauders. This video is going to be about polyprotic acids and how to find the pH and concentration of a weak polyprotic acid. So what are polyprotic acids? Well, polyprotic acids are ones that have more than one proton to donate. So I guess a common example would be H2CO3, which is carbonic acid. So the way carbonic acid dissociates is that it will first give away one of its protons. So one of its protons will be donated to a water. And then what will be left is your conjugate base, which if we lose one of the hydrogens, we'll have one left. It'll be CO3 with a -1 charge. All right, so some of the carbonic acid will lose one hydrogen and look like this. But now this can come down here and act as an acid. So if we have HCO3 minus, this still has one hydrogen that can be lost. And so some of these will go ahead and lose another hydrogen. And then they'll make the conjugate base CO3 with a -2 charge. So the first hydrogen is always lost much more easily than the second. So this is an equation for it losing the first hydrogen. And then after it's lost the first hydrogen, it can lose the second hydrogen. So the equilibrium constant for this one would be Ka1. And then for this one, it would be Ka2. Ka2 is always much, much smaller than Ka1 because it's always harder to lose, or less of these lose the second hydrogen than what lost the first. And so in this equation right here, here's your acid. And here's your conjugate base. And whatever's the conjugate base from that loss of the first hydrogen is going to act as your acid in your second step. And then this will make another conjugate base. All right, so let's take a look at a sample calculation. So calculate the pH and the concentration of all of the ions in a solution of 0.02 molar oxalic acid, which is H2C2O4. Okay, and we were given Ka1 and Ka2. All right, so we're gonna have to write out two equations. So the first equation is gonna be for losing the first hydrogen. So that first one's gonna look like this, H2C2O4. And when that loses one hydrogen, what will be left will be HC2O4 with a -1 charge. All right, and then after it loses that hydrogen, let's just separate this. Then some of these conjugate bases, HC2O4 minus, some of these can act as an acid, and some of them can actually lose another hydrogen. And then it would make the conjugate base C2O4 minus. Okay, so it happens in two steps. This one is going to be using Ka1, which is 5.9 times 10 to the -5. And over here, this is the second dissociation, so this will use Ka2, which is 6.4 times 10 to the -7. All right, so for equilibrium problems, when we're dealing with concentration at the initial concentration and trying to find the concentration at equilibrium, we're going to need to make an ice table. So we'll make an ice table for this first dissociation. All right, so the original concentration of the acid right here, 0.02 molar. These are starting at 0 because we're just putting it into an aqueous solution. All right, so this will be plus x, x, plus x, x, minus x, 0.02 minus x. So everything so far looks like when we're doing the monoprotic weak acids. And then so this equilibrium expression will have the hydrogen on top, which is x. We'll have the conjugate base, which is also x. And then we'll have the acid on the bottom. Just like we did before with the monoprotic acids, when this number is really, really small, we know that this x is going to be small. So we know that this quantity, when you take 0.02 and subtract a really small number, it's pretty close still to 0.02. And we'll make that assumption to make our algebra a little bit easier. We won't have to use the quadratic or anything. All right, so we have this equilibrium expression, and we can use algebra to solve. And when we do that, we get that x is equal to 0.00108. Okay, so what does that mean? That means that at equilibrium for this first association, the final concentration of the hydrogen is 0.00108, and for the conjugate base, it's also 0.00108. So those are the concentrations at equilibrium for these two things. All right, well, that would be done if it was just a monoprotic acid, but it's a diprotic acid, so once it makes this conjugate base, it can actually still act as an acid and lose more hydrogens, donate more protons. So we need to make a second ice table. And so this is where the problem becomes a little bit different from what we've seen with the monoprotic acids. So notice that this is the same as this, right? Whatever the conjugate base was in the first dissociation is your acid in the second dissociation. So we're getting this concentration from right here. This number, 0.00108, is the initial concentration of that conjugate base, which is now the acid. The other thing that's different here is that these are not starting at 0. Okay, the hydrogen has also been produced. It's in the solution. And so the concentration here for hydrogen is coming from right there. So we're transferring this number over 0.00108. That's the starting concentration of the hydrogen. This conjugate base, we don't have any of that present yet, so it looks like this. So this is going to be starting at 0, so the only way it can go is up, so it'll go plus x, which makes x. When this increases, this also has to increase by the same amount, so plus x. So this will be 0.00108 plus x. This will have to be decreasing by x, so 0.00108 minus x. All right, so in our equilibrium expression, we have on top 0.00108 plus x times x, and on the bottom 0.00108 minus x. Just like we did over here, we can say that x is going to be a pretty small number since the k is a pretty small number. And so what I can do here is say that this is going to be pretty close to 0.00108. This is also going to be pretty close to 0.00108. So x is a small number. It's going to change these a little bit, but not enough to make a big difference. So for ease of calculations, let's say that it's just going to look like this. 6.4 times 10 to the negative 7 is equal to 0.00108 times x over 0.00108. All right, and so that assumption is going to be pretty good. You can multiply this out and do the whole quadratic in your calculator if you want, and you should see that it's going to come out to be pretty close to the same. So these cancel out, and then we find that x is equal to 6.4 times 10 to the negative 7. So that x means the concentration of this conjugate base at equilibrium, 6.4 times 10 to the negative 7. The hydrogen concentration will also change by that much. It'll go up by that much. But that number, as you can see, is pretty insignificant. It's not really going to change this very much. So this is your final concentration of the conjugate base. And in our first part of the problem, we found the concentration of hydrogen and the concentration of this conjugate base. And so the last thing we need to do is find the pH. So pH is equal to negative log of hydrogen concentration. And so if we only wanted to find the pH, we could have just stopped here. The only reason we did this second ice table was to find the concentration of this conjugate base at equilibrium. The loss of the second hydrogen doesn't happen very much. So it doesn't really have much of an effect on your pH. So the pH is equal to negative log of the hydrogen concentration, 0.00108. And so our pH ends up being 2.96.